Yes. Hello, everyone. Can you confirm that you can hear me?
Yeah.
Okay, excellent. And you can see the slides?
Yes, I can. Yeah.
Excellent. Yes, hello, everybody. So Michael did the introduction. I won't bother. So I've been doing this project on simulations, and the idea was to compare to Go Green and see how any of them actually perform. Because if you're not familiar with hydrodynamic simulations, the main focus has been on redshift 0 field effectively. Very few have looked at clusters, and especially clusters at redshifts above 1, mostly because there was nothing to compare to, but also because it's quite hard and it's challenging enough as it is. But nevertheless, the claim of all of the simulations is that they do reproduce realistic galaxies, and by redshift 0, they all arrive at somewhat a realistic universe. But the way they get there, nobody's looked at. So I thought I would do that. So that's my little introduction. I think I've mentioned everything. The number of available observations to compare to is limited, even with Go Green at the stage that we're at. So not all plots have data points on them. So just bear that in mind. And everything I talk about is at redshift 0, or not 0, it's redshift 1, so there's no redshift 0 stuff. And all the galaxies I consider are 10 to the 10 solar mass, and what I call as a non-star forming quenched galaxy will be defined by a specific star formation rate, and that's below, I guess, minus 12, just before I begin. Right, so there are lots of simulations to choose from. I've selected some of the main ones, the ones that I had access to most easily. They're all hydrodynamic simulations. And there are two main flavors of them. They are the SPH-based and the adaptive mesh refinement-based. Very different approaches, but the methods have been nailed down, and the actual errors from that are fairly insignificant when compared to the astrophysics. So they are quite comparable at this stage. On the SPH side, there are quite a few. Bahamas is focused mostly on cosmology and large-scale structure, but the galaxies above 10 to the 10 in solar mass, they are still realistic. As you can see, the resolution is rather low, so yeah, so you need to keep that in mind. Now, that's a classic sort of cosmological volume simulation. It is limited, and so the number of really massive galaxies as we have with Go Green, or massive clusters rather, is very small. It's, well, still small. So I supplement this with Maxis, which is a zoom simulation where you use a much larger box used for a dark matter simulation, and select the structures that you know are going to grow into really big ones, and put a box, a hydrodynamics box around them, and re-simulate them again using Bahamas physics. So these clusters are directly comparable to those in Bahamas, and you can supplement them. So they don't look very different at all. So that's excellent. Means that I can have a field sample from Bahamas and some of the lower mass stuff, but there are some really massive structures in Maxis that I can use. Now, Eagle is, everybody's heard of it. That is a rather small box, the AGN-DT9 model. I choose this because the standard Eagle, the X-ray luminosities of groups and clusters were too high. When they were calibrating the models, the amount of gas being ejected wasn't quite enough. So they ran another model where they cranked up the AGN slightly, and so that's a smaller box, but it's more accurate in the cluster regime. Unfortunately, the box size is rather small, so again, I supplement with a similar Zoom simulation, that is hydrangea, part of the Cluster Eagle project. But unfortunately, the mass range is rather different. So at the sort of go green masses, there are only 11 halos from the Zoom simulation. So the combination is still usable, but it's not quite as large as this. Whoops. So just that to bear in mind. And the last one is the TNG 300 simulation, which is a classic box. There is no Zoom simulation for that, but it's still sufficiently large that there are some halos to choose from that are comparable to Go Green. Right, so these are the simulations. I'll talk about the specific selections from them because it is quite important. Right, so these are the sort of halo mass distributions that you get from them if you look at Go Green. So now I should say, I only use what I call the clusters in Go Green. So I truncate everything to 10 to the 14 solar masses in halo mass, or M200. This is to compare more to Remco's work that was being done, and also on the low mass end, you start running into resolution limits in the case of Bahamas, and you need to make a choice somewhere. So I chose this limit, and so in Go Green there are 11 clusters of this mass, and they're quite sparsely distributed over this range. Some are really massive, and Bahamas has this distribution, so it runs out of really massive halos. But if I supplement it with maxes, there are really quite a few to choose from. And so in all of the plots that follow, I either plot a running median, or with an error bar attached to it, or if I compare directly to Go Green, I draw multiple samples of 11 halos from all of these to match the Go Green halo mass function, well, this distribution, and I can attach an error bar now. So there's a way to gauge the sort of the errors on the selection, because we have the numbers. The other two simulations don't do quite so well. TNG just runs out of really massive halos. So in some cases, I am limited to just selecting the most massive 11, or selecting these and then somehow sampling this range for hydrangea. I have no choice but to select all 11 most massive halos, but still missing the most massive end. And then Eagle itself the box doesn't contain any halos above 10 to the 13 in halo mass, or M200. So it doesn't appear here, but it's still useful for a field measurement. So there's some things to bear in mind, that the selections are not completely uniform. Right, so what am I interested in seeing? So there are two classes of what I'd like to look at. One is stellar content of halos. And this is something that I'd expect the simulations to get somewhat right, at least, because all three models at least look at the galaxy stellar mass function, the field galaxy stellar mass function, as the simulations are run, to see if they make sense. So especially this first one, I'd expect them to perform reasonably well. Then the cluster galaxy stellar mass function, that may be slightly different, but still okay. And then the stellar mass to halo mass plot or relation, and galaxy stellar mass functions. But then I would like to also look at, because of Go Green, how does quenching occur in the simulations? And we know that even as Redshift 0, they struggle to reproduce what's observed. And so the question is, how do they do at Redshift 1, where it appears that quenching acts somewhat differently than at Redshift 0? So I do a few tests of that. So star forming and quenched galaxy stellar mass function that Remco has done that I can compare to. Then I have the quench fraction stellar mass plot, and then quench fraction excess, again, comparing to Remco's work. Right, so test number one, field stellar mass to halo mass relation. Here I'm comparing to one observational result and two these are abundance matching results with a bit of modeling. So there are these dashed curves in both plots. Well, in this one and then copied into this one. These are the three simulations. And this is, on the left, you have stellar mass measured within a spherical aperture of 30 kiloparsecs, which is this number chosen to best match observations at redshift 0, and it appears to work quite well with observations in this case. It seems like that's the kind of range where observations can measure stellar mass to within. Whereas on the right, I use the total, which is using the all of the stellar particles which are bound to a halo, and that's the stellar mass that's measured. And the difference between them, what you can see is that the low mass regime is not affected all that much, but there's a deviation at the high mass end where those particles are simply cut out of this plot. So that's something to bear in mind, and other plots I stick to using the 30 kiloparsec stellar mass. Right, so as far as this plot goes, what you see is that the three simulations, they are similar to one another. There are some subtle differences, but they're on the sort of level as what you see in the abundance matching results. And Bahamas appears to match one of them and seems to match some of the go green measurements, although it doesn't quite stretch that far. Because this is a field sample, I don't use the Maxis halos, which would bring it up to this range, but they are specifically selected, so so I exclude them here. But it doesn't do all that badly. And when it comes to the total, there is an upturn in the high mass, as you'd expect, but the amount that each simulation turns up is more for Bahamas than it is for TNG, suggesting that Bahamas halos are less compact. So more of the stuff is getting cut out by imposing this 30 kiloparsec aperture. So that's something to bear in mind, and that's influenced by the implementation of feedback. But that's okay. So field stellar mass content works okay. Now let's look at the stellar mass to halo mass relation for 4 different scenarios. In the top, you have all of the stellar mass contained within R200 and as measured within 30 kiloparsecs, whereas on the right-hand side, you have the total measurement. So what you see here, there's a deviation of Bahamas being this line here. The stellar mass is lower than the other 2 simulations, whereas when you measure it with the total, when you measure the total stellar mass, they are in close agreement, which again says that the halos are less compact in Bahamas. Now, if you just look at the BCG and measure its stellar mass within 30 kiloparsecs, you see that Bahamas, again, is lower than the other 2 simulations. But interestingly, it matches the go green result, which is a bit odd because that's not what we expected before we plotted the go green result. Normally, you'd expect that the simulation with the lowest resolution would struggle because of the feedback, the way it's injected, you heat particles, and because particles are the most massive in Bahamas, the feedback goes into big lumps, and it just behaves differently and slightly in a non-physical way when you have these huge dumps of energy. But for whatever reason, it appears to match go green better. Again, interesting. I haven't looked as to why this happens. This is probably a project in itself, but that's an interesting observation. And again, if you look at the BCG total stellar mass, all of the stellar particles, the simulations seem to agree. So again, BCGs in Bahamas as well as the halos seem to be less compact in Bahamas, but seems to agree with Go Green relative to the other two simulations. Now, the total stellar or galaxy stellar mass function. So again, you'd expect that to agree because all three simulations at least monitor that as they run the simulation and the parameters that they choose. In the field, the Bahamas and TNG, which is this yellow line, they do okay. The most massive galaxies seem to be a bit more massive in TNG, and that's a feature that I see everywhere. Eagle does well on the low mass end, and it quickly runs out of massive galaxies. But you'd expect that the model would do okay in this regime. Cluster-specific galaxy stellar mass function, that's not something that they calibrate on, but it seems to do okay for most of the range, except for the most massive end. And these are the BCGs, the central galaxies. And what I'm finding is that in all three simulations, they are both too massive to different extents. TNG seems to suffer the most from that. And also they're all star forming. Almost by definition, if it's a BCG in a cluster, it seems to be star forming, which suggests that there is some unphysical cooling, gas injection, something going on that doesn't stop star formation in the BCGs. That's something to possibly look at in the future. Right, so this is moving to the second class of tests, which is splitting the galaxy stellar mass function by type. So star forming and quenched galaxies, each row is now a different simulation. And on the left, you have the field stellar mass function, and on the right, you have the cluster stellar mass function. In the field, so I should say the data points are Go Green data as measured by Remco. And what you see is that the simulations are not miles away, but they don't completely reproduce it. In some cases, the trends are not quite right. The curves don't, the dominance of each curve doesn't change for Bahamas, for example, doesn't for TNG. Well, Eagle just doesn't have enough galaxies to fully capture this. In the cluster, things get even worse. You see all kinds of different behaviors that just don't match what's observed. So there's a clear lack of physics, or physics being wrong in clusters. The way galaxies quench in clusters at this redshift, which is indicative that there's something lacking. And there's no point looking in the detail of these curves. Right, so quench fraction against stellar mass, so that you can see that this, you can kind of expect what you're going to see from those other curves. In that, in the field, we see as a function of stellar mass, none of the simulations reproduce the trend of Go Green, which is that of increasing quench fraction with stellar mass, which exists at redshift 0 and at redshift 1. Simulations seem to produce a very flat curve that doesn't scale with stellar mass. And we see this, to some extent, we see this at redshift 0 as well, but it does turn up a bit, maybe not quite enough in the field. Now in clusters, it gets even worse, where Go Green, the quench fractions are still scaling with stellar mass, but scaled up, whereas the simulations show a decreasing quench fraction. Now this end, I already said, that's dominated by the centrals, the BCGs, and they are nearly always star forming, so you'd expect them to drop here. But this regime is very well sampled, especially in Bahamas and Maxes, but yet nearly all of the small galaxies in clusters or low mass galaxies are quenched in the case of Bahamas, and the quench fraction seems to decrease with stellar mass, which is really odd and clearly not correct. And so for quench fraction excess now, so this is capturing just the cluster behavior relative to the field. In go green, you see this increase, which is different to what's been reported for redshift 0. But the simulations either show a somewhat flat profile or a completely decreasing profile with stellar mass, which is again in strong disagreement with observations. And clearly that suggests that the physics of galaxy quenching isn't quite there yet. How much time do I have? How long have I been talking to? Do I have time to talk about selections?
Yeah, you can have another 5 minutes.
Okay, so another thing that I've been looking at is, in the case of Remco's study, the galaxy members were selected on this quite a rigid selection of them being between a 1 megaparsec in the radial direction or tangential direction, within a 1 megaparsec aperture, and a cut in redshift relative to the cluster of 0.02. And that's been applied to every single cluster. That has the potential of introducing some contaminants from the field, adding galaxies which are not really part of the cluster, but counting them as members. And I did this study where I introduced this in the simulations. That's the one thing they do get right, and you can't do these tests in the simulations. And compared this to the friends of friends selection, which is used very widely. It's finding members by linking them with a fixed length, and it may not be the true membership, but compared to what the observations can achieve, it can be considered a lot closer than anything can be done. And so the long story short, what I'm finding is that by doing that, there's an excess of star-forming galaxies being introduced into the sample at low stellar masses. So if I just scroll down to the bottom here, so this is a galaxy stellar mass function. These are star-forming and quiescent, and the triangles are the friends of friends members, and the squares are the observational selection. And what you see, if you look at the difference, there is up to a factor of 4 at the lowest stellar mass, or 10 to the 10, of star-forming galaxies in the cluster sample, whereas the number of quiescent galaxies is the same. And that has the effect of changing the quench fraction, well, changing it by just a bit, actually, here, making it lower. But when you look at quench fraction excess, that's the gray points here, and it doesn't actually change the final result. Right, so I'll just conclude by saying that simulation, as expected, simulations do okay at getting the stellar content right when compared to observations. We see some differences between the 3 different simulations, such as the BCG size, which oddly matches observations. The total galaxy stellar mass function is more or less consistent with observations, but we see big differences the moment we start splitting them by type, star formation activity, and quench fraction estimates are just completely off, which suggests there's some physics still missing in these simulations. And that's at redshift 1. A similar thing is seen at redshift 0, although less, because they've been calibrated on quantities at redshift 0. But the way they get there isn't quite right. So there's still work to be done. And I think I'll finish there, if anyone has any questions.
Thank you, Egidijus. Great stuff.
Thank you.
Good. So we can take some questions on this in particular before moving to general discussion. There was one question in the chat from Ria Silvia. How do you separate the BCG from the intercluster light in the simulations?
So the BCG is flagged up as the central by, is it the subfind algorithm? So there will be one central galaxy which sits at the gravitational potential well. And so it's all done gravitationally, so there is no, well, intercluster light isn't really a problem because it's not done from images. So yeah.
But you also you measure the stellar mass within like an aperture, right?
Mm-hmm. But so the BCG is a dark matter halo, and so all the stellar particles bound to that will be flagged up as the BCG. And so this aperture is then applied to all the particles which are already bound to that halo and no other particles. So I can only exclude stellar particles and not include them. So does that make sense? So these particles are definitely bound to the BCG or the central galaxy.
Yeah, but the ICL will be as well. So the 30 kiloparsecs aperture will help, of course, because the BCG usually is larger than 30 kiloparsecs. But as soon as you go further outside with the stellar mass, it's really difficult. And that's one of the big issues I always see when we compare the simulations and the observations to the BCGs. Because it's always different depending on which observation is used, which stars are actually called to be the BCG. And for the simulation, there's no straightforward way to split this up, because what subfind locates to the BCG includes also the ICL. You have the double component always in the velocities.
Right. So I guess it's just as well that I use the 30 kiloparsec stellar mass.
Yeah, I think that helps. And also, you know, observationally, we haven't tried to do anything special about measuring the total magnitudes or masses of these BCGs. These are the same. The stellar mass we're using just comes from the total K magnitude from source extractor, and then the mass light ratio from aperture colors. And so if one really wanted to do a careful comparison between the simulations and data, you would want to do those two things a little more carefully. So I don't necessarily get super excited about the differences between the stellar masses of those BCGs. They're difficult to measure in both the simulations and the observations. I agree. So we've got a question from Liza Sasnova. How is the compactness of go-green galaxies measured?
I'm guessing this is referring to the BCGs. Here?
I think yeah.
Just BCGs, just general galaxies.
Sorry, so what's the origin of your question? What, in what context are you talking about the compactness?
I was looking at the conclusion slide, and I think it's coming from this plot that the galaxies in Go Green are less compact than in TNG, but as compact as they are in Bahamas. So I don't mean just the BCG, I guess. But if you're only looking at BCGs, then my question's answered. I was wondering if you looked at all of the galaxies or just the BCG.
No, I haven't. But now that you mention it, having seen this result, I think it would be worthwhile if it's possible.
Good. Any other questions directly for Egidijus before we open up to broader discussion? Okay, great. So we have, so that's the end. And first of all,